Welcome back. This video will look at concepts from section 6.4 regarding kinetic energy and 6.5 regarding power. Let's first think back to some concepts learned earlier in the chapter. Remember that work is defined as the scalar product between force and displacement. That was equation 6.5. And if we think about the work done by gravity when something moves, and here you can see in this middle picture, I'm having it move at some arbitrary angle. It could be going straight up, straight down, it could be going sideways, doesn't matter. But there's its displacement vector, and this is the weight. Now don't confuse lowercase w with uppercase W. So this is the weight, which is the force of gravity, and it's always going to be pulling down. And there is some angle between displacement and the force, which is the weight. And here I've made up be the positive y direction. And so capital W, the work done by gravity, is the scalar product, so it's the force of gravity, which is the weight, mass times g, times the displacement times the cosine of the angle between those. Now let's look at an example. We're going to drop a rock from a height of 2 meters, and it's a 4.5 kilogram rock. So let's think about what is the work done by gravity. Here you have the displacement vector and the weight, which is the force of gravity. And it's very helpful to draw a diagram in these situations. So the work done by gravity is, we'll use the equation in the middle of the page, the mass of the rock times g, 9.8 meters per second squared, times the displacement, which is 2 meters, and then times the cosine of the angle between those two vectors. It's a 0-degree angle, and so cosine of 0 degrees becomes 1, and we get that gravity did work of 88.2 joules. And I'm going to emphasize that that's positive 88.2 joules. So here at the top is the work we just did, but now let's pick up the rock and lift it back up 2 meters. We're going to bring it back to its original location. Let's think about the work done by gravity, not the work done by us as we're lifting, but again, I want to focus on the work done by the force of gravity. So the work done by gravity is the same. We'll use the equation you can see at the top of the page. So the mass times g times displacement, but now look at the picture, it's an 180-degree angle between those, so times the cosine of 180 degrees, which is -1. So the work done by gravity in this case is negative 88.2 joules. So for the total round trip of the rock, as we first dropped it, then we brought it back up, gravity did, first it did 88.2 joules of work, then it did negative 88.2 joules of work, and so gravity did 0 joules of work for the round trip. Or more simply, we could have, if we just wanted to know what is the work done by gravity for the round trip, we could have gone to the equation at the top of the page and plugged in a displacement of 0, and that would have given us 0 joules of work. Let's use this example. Let's say a force of 13 I hat plus 13 j hat newtons is applied to an object while the object moves from position 0, 0 to position 4.2 and 2.1 meters. Calculate the work done by the force. Well, here I've written out the given information. It's helpful to draw a picture. There's the force vector, there's the displacement vector, there's some angle between them. And in the previous example, we used work is equal to force times displacement times cosine of the angle. It would take a little bit of work to find the magnitude of force, then the magnitude of displacement, and then that angle. But remember that it comes from this definition that work is equal to the dot product of those vectors. So here it's useful to remember that dot product is the product of the x values plus the product of the y values. So it's much easier, given the given information in this problem, to use this formula here, that it's x component of force times delta x plus y component of force times delta y. And so we can say 13 newtons times it moved in the x direction 4.2 meters plus 13 newtons, which is the y component, times it moved in the y direction 2.1 meters, and we get 81.9 joules. And that's a much easier method than using this equation, which would have needed to find the magnitudes of the two vectors and that angle. The work-energy theorem is given in section 6.4, which also explained kinetic energy, but here I give it to you very briefly. And it says that the change in an object's kinetic energy is equal to the net work done on the object. And the derivation in the book comes from here, that the net work is equal to 1/2 mv squared minus 1/2 m times the original v squared, of course m being mass and v being velocity. So we define kinetic energy, this very useful concept, as 1/2 the mass of the object times its speed squared. And notice that it is a scalar. So the net work done on an object is the final kinetic energy minus the original kinetic energy, or we can call that the change in kinetic energy. Here at the top are those three equations again. What this means is that when the net work done on an object is positive or greater than 0, it will accelerate because final kinetic energy is greater than original kinetic energy. So acceleration is positive. When the net work done on an object is 0, then there will be no acceleration. It'll be going at a constant speed. And when the net work done on an object is less than 0, that means that the final kinetic energy is less than the original kinetic energy, so it'll slow down. Acceleration will be negative. So now let's relate this to the example of a ball that is thrown straight up in the air, and then it falls back down to its original position. While it's going up, there is only one force acting on it, and that's gravity. So the work done by gravity is the net work done on it. Gravity does negative work. And so you can see displacement is up, the force of gravity, which is the weight, is down. There's a 180-degree angle in there. And as we've seen before, there was an example with a rock a few pages ago, that gravity is doing negative work. So the net work is negative. And that relates to the acceleration. The acceleration, therefore, is negative. And we know that when you throw a ball up in the air, the ball will slow down as it goes upward. Now, the ball then starts to come down. You can look at the picture. You can see the force of gravity is down. The displacement is down. So gravity is doing positive work because those vectors are in the same direction. So the net work is positive, therefore the acceleration is also positive, and the ball speeds up. We now look at section 6.5, which is on power. Power is defined as the rate of energy transformed, or work, that is done. So here's the simple equation for it, that power is the work done divided by time. Now, I wrote up at the top energy transformed. Right now, we're going to think of it in terms of work done, but as we continue in our study of physics, we're going to see it can be more than just work done. It can be more, generally speaking, energy transformed. It could be heat that is transferred from one place to another. It could have to do with electrical energy, or a variety of different kinds of energies that are either turned from one form to another or are moved from one place to another. But for now, we'll just say that power is work divided by time. Its units are joules per second. A joule per second is known as a watt, and this is named after James Watt. And by the way, James Watt invented a unit of power called the horsepower. So in case it comes up in any of your examples or problems, 1 horsepower is equal to 746 watts. So let's say we lift 100 kilograms and we lift at a distance straight up of 20 meters. Now the work done is, you already know, it is the force we apply times the displacement. So we do 19,600 joules of work. 100 kilograms times 9.8 newtons per kilogram times the displacement of 20 meters, and we get 19,600 joules. Now the power is that work divided by the time. And the quicker we do it, the more power it takes. So if we lift that 100 kilograms up 20 meters and we do it in 1 minute, then the power is 19,600 joules divided by 60 seconds, and we get 327 watts, which is about 0.44 horsepower. Now, if we do it more slowly, if we do it in 10 minutes, then we're going to divide the 19,600 joules by 600 seconds, and we only get a tenth the amount of power, 32.7 watts. If we do it more quickly, let's say we can lift it in 10 seconds, then we take 19,600 joules divided by the time of 10 seconds, and we get 1960 watts. Be careful now that we're not confusing our W's. We have uppercase W as a quantity that means work, but now we have it as a unit that means watts, and that's a unit of power. Now, as I mentioned a few minutes ago, power can mean more than just work over time. In a more general sense, it can be energy over time. So we can talk about electrical power. We can talk about the power generated as you exercise that might be measured in calories per minute or calories per hour. It could be radiative power coming out from the sun or a light bulb. It could have to do with heat loss that we'll get into later on. Now, if power is energy per time, we can also say that an amount of energy transformed is power times time, and the electric company measures this not in joules but in kilowatt hours. Now think about those units. Dimensionally, that makes sense that would be a unit of energy. It's power times time, so kilowatts, which is a unit of power, times time, which is hours. Quick example, how much energy and the cost to run a 10-watt light bulb all year long? Well, sometimes it's easier not to convert to MKS units, which are joules, and let's use the units as they're given, 10 watts for an entire year. So energy is the 10 watts times, let's get this in watt hours because the power company charges us per kilowatt hour. So 10 watts times, there are 8760 hours in a year, and we get 87,600 watt hours. Divide that by 1,000, we get 87.6 kilowatt hours. Now, the power company, if they charge 20 cents per kilowatt hour, will multiply that by 20 cents, and we get a total cost to run that light bulb all year long of $17.52. You've already seen this equation, that average power is the amount of work done divided by time. Here I've used the delta notation to denote increments of work and time. Often the rate of doing work varies with time. We need to define instantaneous power as the average power taken in the limit of an arbitrarily small time interval delta t. So let's think of power, instantaneous power, as being the limit of delta W over delta T, and that becomes dW dt. Now, when power is constant, then average power is the instantaneous power. It's not going to change. So we can just say that work done is power times the time increment. Work done is power times delta T. However, when power is not constant, we're going to consider the small amounts of work delta W over small delta T, and so the work becomes the limit of the sum of P delta T, and that becomes the integral taken between the time limits of T1 and T2 of P dt. So here are our two work equations. The one on the left is the simpler one. When power is constant, we can just say work equals average power times time. But when power is changing, we're going to need to use the integration. So with that in mind, let's look at this example, a problem in the back of the book. It says, by measuring oxygen uptake, sports physiologists have found that long-distance runners' power output is given approximately by P equals M times BV minus C. M and V are the runner's mass and speed. B and C are given in the problem. Determine the work done by a 54-kilogram runner who runs a 10-kilometer race at 5.2 meters per second. All right, so we'll first write out the equation that's given. We have all the given information. One thing that's not explicitly given to us, we're going to need time at some point. And so speed is distance over t, which means time is distance over velocity. It says 10,000 kilometers at a speed of 5.2 meters per second, so we can get the time of 1923.1 seconds. All right, now we have these two equations to choose from, and at first glance it seems because power is given by a formula, we might be inclined to think to use the integration, but what we have to consider is the question, is power changing with respect to time? And no, it's not. Time is not involved in that equation. So as we choose between these equations, we're going to go for the non-calculus one, work equals power times time. And so we plug in that formula for power, and then we can plug in all the given constants, and what we end up with is work is 2.12 times 10 to the 6th joules. Now we can convert that to calories if we're interested, and 2.12 times 10 to the 6 joules multiplied by 1 food calorie, which is actually known as a kilocalorie, divided by 4184 joules, and we get 506 calories. That is the end of chapter 6. Have a great day.